Have you ever wondered how your computer pulls off something as complicated as math when really it's all just a bunch of on-off switches? Well, the secret is hiding inside a tiny component called a decoder. Today, we're going to pull back the curtain and see exactly how this little building block turns simple code into the powerful logic that runs, well, pretty much everything. So here's the game plan. We're going to start with the basics. What exactly is a decoder? Then we'll uncover its hidden superpower that lets it build basically any logic function you can dream up. After that, we're putting it to the test with a big challenge, building a full adder, which is the heart of all computer math. And finally, we'll zoom out and see where these incredible little devices are hiding in the world all around us. All right, first up, let's meet our star component for the day. I want you to think of the decoder as this highly specialized digital agent. You give it a secret code, and it knows exactly which one and only one action to take. I mean, really think about that for a second. Your computer has billions of tiny little mailboxes for data. So how in the world does it pinpoint the exact one it needs, instantly, without getting lost? How does it zero in on that single address and ignore all the others? You probably guessed it. The answer is the decoder. Okay, so here's the official textbook definition. A decoder is a circuit that takes a small number of inputs, we'll call it n, and it uses that code to manage a way bigger number of outputs, specifically 2 to the power of n. So get this, a tiny 3-bit input can control 8 separate outputs, and a 4-bit input can control 16. It scales up really fast. And this little diagram just explains it perfectly. On the left, you've got your n input lines. They carry a binary code, kind of like a street address. The decoder reads that code, does its thing, and then activates only one of the 2 to the n output lines on the right. It's a specialist that, when given a code, points to one single destination. That's its whole job. And check this out. This is a truth table for a real-world decoder chip. No matter what 3-bit code you give it on the left, from 000 all the way to 111, just look at the outputs. Only one of them is ever active at a time. See that? For any given input, you get one active signal out. That's the decoder's signature move. So being able to pick one thing out of many is super useful, for sure. But that's not the whole story, not even close. This simple function is hiding an absolutely incredible superpower that lets us build almost anything we want. This right here, this is the secret. Every single output line from a decoder perfectly matches one specific combination of its inputs. And in the world of Boolean algebra, we call each of those unique combinations a minterm. So a 3 to 8 decoder doesn't just have 8 outputs, it's really an engine that can generate all 8 possible minterms for 3 variables. And this is where it gets really, really cool. You see, any logic function, no matter how complex, can be described as a sum of these minterms. And since a decoder can generate every possible minterm, well, that means a decoder can be used to build literally any logic function. It's a universal logic building block all in one little chip. And believe it or not, the process is dead simple. First, you just figure out your logic. You make a list of which minterms need to make your function true. Second, you grab a decoder that has enough input pins for all your variables. And third, you just take all the minterm output wires you need from the decoder and feed them into a simple OR gate. That's it. The OR gate's output will now perfectly follow the custom logic you designed. Okay, theory is great and all, but let's put this superpower to the test, right? Our challenge is to build one of the most important, most fundamental circuits in all of computing, the full adder. Seriously, every single time your computer does math, at the deepest, most basic level, it's using circuits just like this one. This isn't just some textbook problem. This is the literal foundation of how computers compute. Its job is simple but absolutely critical. Add 3 single bits together and give us 2 results, a sum bit and a carryout bit for the next column. This truth table shows us everything it needs to do. For example, if we add 0 plus 1 plus a carry-in of 0, the sum is 1 and there's no carry. Makes sense. But what if we add 1 plus another 1 from a carry? Well, that's 3, which in binary is 1, 1. So the sum bit is 1 and we have to carry a 1. This table is the complete blueprint for the logic we have to build. So this is basically step 1 of our plan. We just go through that truth table and write down which input combinations, which minterms, make the sum output a 1. Turns out it's minterms 1, 2, 4, and 7. Then we do the exact same thing for the carry output. That's 1 from minterms 3, 5, 6, and 7. We now have our recipe. All right, it is time for assembly. We have our blueprint, we have our components. Let's wire this thing up and actually create a circuit that can perform binary addition from scratch.
Okay, here's our main component, just like step 2 told us, a 3 to 8 decoder. We're going to feed our 3 input bits, X, Y, and Z, right into the input. This chip is now armed and ready to spit out every single minterm we could possibly need for this problem.
And now watch this. For our sum output, our blueprint called for minterms 1, 2, 4, and 7. So we literally just take those 4 output wires from our decoder and connect them all to one OR gate. And boom, just like that, we have our sum output.
Now we just rinse and repeat for the carry output. The blueprint says we need minterms 3, 5, 6, and 7. No problem. We just grab those lines, wire them into a second OR gate, and that's it. We're done. We now have a working carry output.
And just take a look at that, the finished product. A fully functional full adder, the very heart of computer math, built with just one single decoder and 2 simple OR gates. I mean, how elegant is that? It's the perfect showcase of the decoder's real power as a universal logic builder.
Okay, so we've built something pretty amazing here, but this whole technique, it's not just a cool party trick for textbooks. Decoders are absolute workhorses. They're everywhere, silently and efficiently doing their job in the technology we rely on every single day.
And the list of where you find them is just incredible. I mean, from selecting memory addresses, which is where we started this whole conversation, to routing data packets across the internet, they're inside the control unit of your computer's brain, the CPU. They're in barcode scanners, security systems, even in the controllers for traffic lights.
Here's a perfect example you have definitely seen before. You ever look at a digital clock or a calculator and wonder how it turns a number in its memory into a shape you can actually read? It uses a special kind of decoder. It takes a 4-bit code for a number, say 0111 for the number 7, and it figures out which of the 7 segments on the display need to light up. It's decoding a number into a visual pattern.
You know, when you boil it all down, understanding the decoder really shows you how something as amazing as computer arithmetic can be built from simple, elegant modular parts. It really makes you wonder, right? If this one little component can build the logic for all of math, what other incredible fundamental building blocks are out there, just hiding in plain sight? Thanks for joining me.